Okay, welcome back again. I guess you guys have already started your assignment to continue our lecture. I think we have a bit more time. The lecture, in fact, also to do the assignment. This particular week, we are going to see chapter 6, precisely rocket control. Now, what is important in this particular chapter is that to really understand the difference between rocket control and, of course, an aircraft control, satellites control. So, after particularly this chapter, you may see how you can ensure a rocket flies, or rather how a rocket flies, and how you want to control the path of the rocket. And you should be able to also see the difference between an aircraft, for example. You have also done satellite technology, and I believe you still remember how basically satellite flies and how actually it maintains its trajectory. So in this particular chapter, we are going to see how we can ensure the rocket is flying according to the path that we have designed. That's the most important thing. Now, it is also important to understand that this is a very huge subject, rocket control itself. Well, sharing my experience, I personally have done one whole semester of rocket dynamics and control. So what I've thought that this is very, very important. So I have given a sort of a snapshot of what is very, very important. We don't go into too much on the derivatives or other derivations. We will look into the fundamental and try to understand what is very, very important and how actually we can control the rocket. It can go very, very deep. You can even spend one whole semester studying rocket dynamics and control. But as I've said, rocket technology is encompassing not only rocket control but all the other elements of rocket as well. So you will get the overview. After this, then we are going to migrate to re-entry as well. So therefore, you need to have a bit of knowledge on how basically to control the rocket. Now, it is a very, very complex topic. More importantly, the definitions first for rocket dynamic. All these are very important parameters, and all these parameters is going to appear throughout your lecture slides. And throughout the lecture, basically this is what you're going to see. I'm not going to do a cross-reference. I hope that you can understand all these actually parameters well, and in order for you to read together with the equations that I'm going to present. Now, more importantly, if you look at it, let me go through maybe a control thrust. This is a very, very important parameter for rocket control, because this is where the thrust is available for us to push the rocket to fly. Okay, this is very, very important. And you have also non-control thrust that I will show you afterwards in the diagram that we have. Center of gravity, force, articulation of nozzle. You will see afterwards how basically we can ensure that the path of the rocket can be changed to a desirable path. You have a nominal trajectory plane. This is basically a definition of a plane to define the actual rocket model that we talk about. This is the launcher's plane. This is incident. I will show you exactly this incident. This is just an angle. These two parameters are very, very critical. One is basically very crucial, in fact, and critical. Nozzle control and basically the angle. This you can see is that desired angle that you want the rocket to fly. So pay extra careful or extra attention to these two quantities: the nozzle control angle beta and the angle, the flight angle that you want to actually fly to, which is the rocket trajectory. This is the phi. Then you have all the other parameters such as wind velocities, which is just always, especially when you fly the rocket in the atmospheric layer. You have velocity with respect to the plane. We define it z dot. You have a propulsion acceleration. This is important also. And you have the velocity, the flight direction f. Basically, this is your z direction. Inertials of the nozzle, inertia without the nozzle, inertia of the nozzle, mass of the nozzle, mass without the nozzle. And
important parameters. This is going to help us in order to find the exact torque. So you need to know the lever arm, so to say, from the center of gravity nozzle to articulation distance. Articulation distance is articulation of nozzle distance. So when you have a nozzle, basically, articulation means you should be able to do this. This is articulation of nozzle. I'm very sure you have also heard a term vector thrust vectoring. So if in an aircraft you do thrust vectoring, in commercial aircraft you don't do that, but in a combat aircraft you do thrust vectoring. And when you talk about thrust vectoring, then you will see that nozzle articulation at this manner. Okay, or this. This basically to alter your thrust direction. And also you have that CG rocket and articulation distance, basically CG of the rocket and the potential force. I will show you exactly where is this potential force and why this potential force is available. You have a dynamic pressure. What is dynamic pressure? If you fly a rocket at a very high speed, you will have a dynamic pressure throughout the skin of the rocket. And dynamic pressure can cause forces. We will see what kind of forces available. This is a reference surface. Surface is referred to the launcher itself. Potential gradient. Now drag gradient. Looks like there are two components which sort of indicates that there is some forces are involved. Potential forces are involved, drag forces are involved. Coupled with the surface, that means the surface of the launcher, we should be able to define those kind of forces. And you have a drag coefficient. When I talk about drag coefficient, I think you already have in mind that, look, maybe he's going to talk about the drag force. Yes, true, there will be two types of major forces that you have because of the dynamic pressure. One is basically potential force, and another one is basically drag forces. All these are external forces because of your speed, because of your velocity. You fly so fast, then you have all this affecting to the body. Now, importantly is this. As I've mentioned just now, nozzle control and angle is what is important. This is at the end of this chapter, you will see how we are going to tie these two quantities together. Now, if you look at nozzle control, as you can see, if I want to actually move the nozzles, then I should be able to move the direction of the rocket. Simple. So when I move the direction of the rocket, which means that there's something actually is going to move the rocket its way that way, right? So this movement, there is a very specific quantities involved. It's torque. When you move the body at a single center, the body is being moved this way. The torque quantity comes into play because the body has a mass. Now, don't forget, at the same time, we are also flying up. That means we have an engine which is pushing us upwards. So which means that there is also force involved, thrust. So there is a force involved, and because of my articulation, what is induced? The torque is actually induced because I have a mass here. So now, if I want to write an equation of dynamics, the rocket dynamics, I think I should take care of these two quantities. I should take care of the force. I should have an equation where it indicates all the forces acting on the rigid body. In this case, it's rocket. Second thing, I should have the complete torque equation. Because as I mentioned just now, when you do rocket thrust vectoring, this is what happens. When you don't have, for example, you don't do thrust vectoring for, let's say, solid boosters. Solid boosters, you don't have this thrust vectoring. It just burns, you ignite, as we have calculated in the rocket fuel equation. We ignite, it burns, the jet flow is created, and you have the thrust, and rocket is basically going to fly up. So that is very easy. Now, if you want to change then, what we do, for example, for liquid propulsion stages, we have thrust vectoring in order to make sure we can divert the rocket into a path actually we want. So this happens. So then always remember these two quantities something like we want to actually talk about the rocket dynamics. So let me, once all these quantities is been defined, explained, so we can move forward to see the actual diagram, how we are going to put into the diagram. Now if you look at this, assume that this rocket, obviously this is not a solid booster, it has to be a liquid booster, liquid propulsion system where I can basically alter my trajectory or my path or my direction of the flight. So as I've said, this is the control thrust that you want. You ignite the engine. What engine that we have studied the engine, liquid engine. You ignite that, so practically the jet flows in and it gives you the actual thrust. So this is basically the control thrust basically. Now this is your articulation point. From here, you should be able to do this. So you know, when you do this, direction of flight is also to be changed. Attention is to be given here. Assume that this is center of gravity for this particular rocket. Center of gravity for the nozzle should be somewhere here. Now, in principle, both the center of gravities are quite close actually. Because if you look at rocket engines, normally at this point you have your payload, which is practically your satellite, or maybe your any cargo that you want to take into space station. So if you look at the rocket calculation, stage 1, stage 2, stage 3, if you look at it, biggest bulk is always in the lower stage, because that's where you have your maximum amount of fuel, booster is full, everything is full. So technically speaking, your center of gravity is always much closer down to the nozzle. It will not be up here for sure. So what I'm saying is that the relative difference between the articulation and the CG, it will be slightly closer. Yeah, this is just exaggerated so that I can draw as I want. So this is uncontrolled thrust actually you have. This is a controlled thrust because when I move the beta angle, thrust comes up. This is where the actual thrust is going to hit me, right? That's how it will go. So this is, and while else you're already flying here, it's practically going to be your controlled thrust. Alright? This is your rocket velocity. Look at this and this. It should be parallel because you are flying up, right? So rocket are going to go into that direction. This is a force. Now this is the incident angle with respect to that x. X is a flight direction. Normally roll, RPY, roll, pitch your z. Assume that planet Earth is here. Planet Earth is here. Z is pointing towards 2. Negative, that means straight to planet Earth, and you're flying up. So remember, I told you that it's a two type of forces acting here. This is the drag force. This is the potential force. Now, why this happens is because of the dynamic pressure of that launching surface, launching system, launching body. Therefore, you will have a skin, so to say, skin is being stressed and induces the drag at one hand, and another one is potential. Means what? There is also, because of your doing thrust vectoring, you are going to also induce potential forces in sideways. Okay? So therefore, these are the two components you have. They are also closely related. In fact, they are quite close if you look at it with respect to the center of gravity. So it depending on the actual launcher. Some launchers, each and every launcher will have this given to you, just like the engine performance, where exactly they are, in that sense. Alright? So this is a simple diagram, and this defines how we are going to take over this. And of course, this wind, yeah, wind coming up here. Now, if you look at this, you can imagine. Now, this is one angle. Now, assume that I want to fly. I want to fly this direction. Obviously, my thrust vectoring will be here. I want to fly that direction. My thrust vectoring should be this side. Okay, there is two things. Now imagine this. So this is quite clear. You are changing your direction of the flight with respect to the thrust vectoring. That's clear. Now remember, there's another thing which is also important to note is technically the attitude of the rigid body. Now what I have shown here is basically for thrust control, thrust vectoring. Now if you say that, look, sometimes the rocket has a slight attitude. That means that they are not exactly on the principal axis because of disturbance, etc. And that is not because of the translation motion, it's a rotational motion. So that you can really correct that. Simple method. You will have, if you look at launches, if you look at all those launches flying, there are small sets of thrusters you can see outside the body. Those are the thrusters used basically to correct the attitude. That means what? Assume that if the launcher is supposed to be like this, but because of maybe some external disturbance, it's like that, right? So you want to make sure that there is back to the actual principal axis. This is a rotational motion. You can't actually do anything else. You can't actually on the engine, and because the engine is not flying, so a rocket will keep on flying this way. So what you exactly do is that you can, for example, if you want to correct the motion, rotational motion along your x, all you have to do, assume this is x, you want to make sure this, you fire up and you fire down, this will rotate. So any rotation you can induce by just not using this, you can't do that. This is only for translation motion. Any rotational motion you will see on launchers, in their body, they have all these small thrusters. As I've said, if you have 3 axes, you can have this principle: fire equally up, fire equally down. It should rotate. Correct? Same force should rotate. So likewise, 3 axes, you want to rotate here, it's easy. Fire up, fire down, fire up, fire down, fire up. So they will rotate to correct the attitude. So that portion is an attitude control, which we are not going to discuss too much. More importantly, if you look at it, is practically the thrust vectoring. Okay? If you want to send a missile, let's say or to hit down an aircraft, then this thrust vectoring and basically the attitude, because of the precision, is extremely important. Right? So, as I mentioned just now, there are 2 major quantities that you want to have. First is the equation, as I said, torque. The torque equation at rocket means torque equation here. Then there will be another torque equation I can write for the nozzle, at nozzle. Because nozzle is also moving, right? Nozzle moving. So there's a torque induced here. Because of this movement, there is this movement. Torque also induced here. So there's 2 torque equations I can write. And the forces. The force, basically, I can also write that force equation generally. F equals to ma, I can also have that. So I have 2 quantities which I want to write. And as written as this is, there is this, I'm just taking that, a deduced form. It starts off not with this, it has about maybe a page up. But this is the deduced form. And then this is for that torque at rocket, this is force for the rocket, and torque at nozzle, if you look at it. So now, the actual frequency for this whole body, if you look at it, you deduce. When I deduce all this, when I have an equation, I put them together, I can actually look at the actual frequency of the actual rigid body. Principally, what I can tell, the frequency is basically governed mainly by these three quantities. And all these quantities are coming from the nozzle. This is the control thrust. This is basically the nozzle's mass, and this is basically the distance between the nozzle and the articulation. If you look at L, this is what you have. There you go. Yeah. Articulation. So if you look at all this, so which means that tells us, so it looks like my frequency of this particular system, this dynamic system. Just imagine yourself, you have learned mass and spring model, right? When you look at mass and spring model, it is exciting because there is dynamics, and you want to know the actual frequency so that you can control it. Okay, the natural frequency that you are looking at. So therefore, each and every system, you also want to know what is the frequency here. So the frequency here is important. This is the quantity that you will get. Now, why is it so important to know this frequency? Now, you are going to put a payload. Assume this frequency is so high, it can even break up your payload. So it's very, very important. Very, very important to know the actual frequency in terms of dynamics, so that you know that you are in a safe regime, and your payload or your satellite will be safe before it actually be injected into that orbit. Now this is also important, this frequency also is important because it also ensures all the other components in the rocket. For example, you have engine system, you have electronics, you have gyroscope. All those, you want to ensure that all these are in a safe regime. So this is very, very important. So the launcher, any launchers would actually provide you that frequency. And now you know how basically that frequency can be calculated. It comes from the actual dynamics of motion. Okay? So let's move forward. Now, let's look at a simplified model. So, you have seen the equations. Now, why I say that I can simplify this model, there is two principles to simplify this model. One, I understand that the distance between the articulation and the center of gravity of the rocket is quite near. So, which means that it's very small. So, likewise, the center of gravity of the nozzle with respect to the articulation is also very, very small. So therefore, that you can deduce this. So when you can deduce this, you can come up with a huge, a simplified model which carries a very, very important parameters. So I define the incident angle. Ki I define is basically the control thrust. Basically, you have the distance, okay, and this is the initial. This is I. Then you have also A6 I define is another force. Okay, this force is quite clear, is a potential force. So we know that this I define it this way so that I can write an equation with respect to the actual two quantities that I wanted. Which one? This articulation and my flight path, or rather the angle that I will get. So there is a relation. So if I can control this articulation, I should be also able to control that actual angle. That is why these two quantities is so important. So now, coming back to this, if you look at the condition, now this I will explain slightly when we reach here. Now this is basically for control engineering, you have done control system. So this is condition where you have this quantity to ensure stability. That means what? The whole system is going to be stable. Now let's move on to this first. Equation of motion, remember the torque and force at rocket. I take that equation. Why? Because those equations have these two quantities. And I deduce these two quantities. I deduce them. When I deduce them, what I should be able to get? I should be actually able to rearrange this. Now, very important, this is in an analytical form. That means it's a time domain. This is in a time domain. All these equations are in time domain. This derivative, time derivatives. All these are in time domain. Now, in order for me to solve this equation clearly, we have also learned in control engineering to use the operator, Laplace operator. So therefore, I have two equations in time domain. I transform them into I use Laplace operator basically to assist me to solve that equation, so that I can know whether they are stable or not. What are the parameters needed for the whole system to be stable? Now, sometimes Laplace operator you use S. Here I am using P. Quite typical. S or P is a Laplace operator. Therefore, the relation between the beta angle, that is the articulation angle, and the flight angle that you have, rocket flight angle, you already established. Now, again, I see all these parameters. I can deduce them. How I deduce them? Something very close. I deduce them. I reach a very simplified form of this. This is a major component which is important. Now, in order for me to ensure that the beta will respond well to the angle needed, I must ensure that this system must be stable. In order for this system, P is again is Laplace, could be S squared also. Okay, Laplace. In order for me to ensure the open loop stability, in order for me to ensure that this is stable, this has to be negative. That means A6 must be less than 0. When A6 is negative, this whole term becomes positive. You want to plot the actual poles, and you will ensure when this quantity is here is positive, you will ensure the poles are in the left side of the imaginary axis. Therefore, the system will be stable. What it means that, look, if I want a very particular angle that I want to fly, safely the system can deliver the beta. For example, I want 300, let's say 360 degrees. I'll give you a very good example. Now, think about this. You want this, right? This is the flight. You want this 360 degrees, or let's say 180 degrees, let's say. It's going to be here, right? You know, what will happen to your nozzle? Nozzle can't deliver that. It goes until maximum and stops, and then it can't deliver, it won't be stable. It won't be stable already. Whereas, everything will be haywire. What is needed, you will not be able to deliver. So in order for us to ensure what is needed and that beta can be safely delivered, we must make sure that the actual dynamics, the open transfer function for these two quantities is basically in a stable manner. I'm very sure you have done control engineering, so this is actually part of the control engineering. So remember, these two quantities, flight angle, beta. You request, I deliver. In order for me to ensure that I can deliver, I'll have to make sure that A6 remains negative here, so that this will be positive here. Okay? Alright, now I want to do rocket control. Good news is that I've already have a simplified model of the transfer function of the rocket, the dynamics. I already have it. Okay. Now, K over, again in Laplace form, you can be S square or P square is a Laplace form, Laplace operator minus A6. This is I picked up from just now. Remember how we got this? We got this from when we start writing the equation. Top equation, then we wrote the force equation, we deduced the equation, and we simplified that. Finally, we got the actual dynamics of the rocket. And we have ensured that the dynamics of it is stable form. Okay, this is important, huh? Now, in order for us to move or articulate, you need a servo, right? You need a servo. In the actual rocket, we use hydraulic basically to move, but it's a servo. You move, you use hydraulics, you can see. You need a servo. So if you look at the actual servo that you have, this is the desired beta that you want to move. This is a control beta that you control. Huh? If you look at the servo's transfer function, it is like a second order system. It is like a second order system. I simplify this. I didn't give you the detail, but I just tell you you can model as a second order system where this phi s is actually a damping or zeta. It means that, okay, what it means, we are just telling you this, saying that, look, it doesn't mean that the servo comes with the damper. No. It just means that system is a second order system. Okay, second order system, then we got x squared. Yeah? P squared, A squared. This is a second order system. Okay. This is a second order system. And if you look at your mass and spring model that you have done in wavy vibration, that is a second order system. And it can be actually written as this form. So remember that. Okay? So it's a second, this is also a second order system. So this is servo. And what I want to know here is that I want to know what is the frequency. The frequency is important, and plus what is also my zeta. So for example, for Ariane 4, the values are given. The zeta basically 0.3 to 0.5 basically. Okay? It is, that means the servo is going to do this. Let's say I need to move here. Servo will go straight, then and just stabilize. You will not overshoot. Okay? That means there's a movement like that. Okay. So 0.3 zeta. Typically, I think I use zeta, I use phi here. And 30 to 40 radian per second, the actual frequency of servos for Ariane. Another, in order for you to control, obviously, you need to sense, right? Like gyro, like in aircraft. You need the gyro. So gyro would also have its model. So what is a model? Again, it is also a second order system. And if you look at the second order system, you look at the frequency 150 to 200. Now look at the damping ratios. It's quite high. It's almost, if it's this damping ratio, if it's equals to 1, practically you meet that point that you want without any overshoot. These are all basically, if it's a 1, then the overshoot is very little already. Okay? Exactly 1, there won't be any overshoot, straight you will reach the point. Yeah, please do refer back to the vibration notes. And obviously, if you look at the frequency of gyro is very high. Because if you want to control something, you need to measure. The measurement system must work at very high frequency, then you can deliver that control system's basically frequency. Now, obviously, the control system frequency must be lesser than this. The servo must be also lesser than 150, correct? Obviously, servo is lesser than that. You sense very fast, then you inject the system. If assume the servo is faster, gyro is actually slower, you will get accumulated errors. And finally, it will become uncontrollable. Okay, now very important, you have learned control engineering. I have the dynamics of the rocket. I have the servo dynamics, the transfer function of the servo. I have the transfer function of the gyro. So technically speaking, the plant is this plant, servo, sensor. I can now build a block diagram. I'm going to build a block diagram. There you go. You have my plant, my servo. This is what you want, right? Plant. Let's go back to our model. This is what you want. This is what you want to control. You want, let's say 5 degrees, I must move beta, maybe 1 degree. Okay? So, command, and this is what you achieve. Let's go back. You have command, beta, the commander is what you want. I command here, servo pushes the nozzle, beta angle is created. When beta angle is created, the rocket is going to move, and I have rocket is moved at this angle, and I want to know how much this angle. I fix one gyro. Gyro gives me the reading. This is the gyro. Now note very carefully, there is two components here, sigma p. Sigma p, P is a Laplace operator, K. Now there is something there which is not being explained here, is that the controller. These are the control gain. So if you look at this, if you write a transfer function for this, it has a PD controller, proportional and derivative control. Proportional gain, derivative gain. We put them all together, we can calculate how much of gain that we must put in here. For example, I want this much of angle. What is the maximum? What is the minimum? What is the gain should I have here? We can calculate that using your control engineering techniques. It's easy. Now more importantly is this, open loop function. Where open loop, this is basically to ensure the stability of the whole system when you put all together. Remember, just now, for our plant, rocket was stable. Remember, we already know what is important, what are the parameters in order for my rocket to be stable. That we have already. Now, if you put everything together, it might be unstable. So, in order for us to ensure that the whole system is stable, we need to run back that actual open loop transfer function. Okay? So, fine. This will give you stability. In fact, here you can actually start plotting your poles. Now, if you have a transfer function, that means what? Your desired phi, your commanded phi. Alright? And what would be your poles? Where your poles would be? You can actually plot already here. And in order for stability, it has to be all in imaginary axis. So, therefore, what exactly that we have done? We have built a very complete block diagram which encompasses the rocket dynamics, the servo for actuation, articulation, the gyro for sensing. Now, this is exactly valid for even your aircraft, but only difference is that the plan will be different for your aircraft. This is rocket. For satellite is also valid, but the plan will be for satellite. So, plan means what? The dynamics of aircraft, the dynamics of rocket, or dynamics of satellite. That you must write equations and develop that. So, ladies and gentlemen, I think more or less I have included rocket control. So, just understand it is a very complex, of course, subject. There is a lot of actual control techniques actually we can learn in this particular chapter. But what I've given you a very quick overview and straight jump into the equation which is relevant, and deduce the equation and pick that and start actually building control blocks, because you're quite familiar with control system already. We build control block, and there you go, we have a complete control loop. Now, if you ask me what will happen if I need to control another axis, you can imagine if you want to have this motion and this motion, you will have two loops of this. You will have two. This and this. You will have two. Okay? So that's quite clear. Now you can do a cascade in order to have two multiple input, multiple output technique. You can have that, and then you can have these two inputs to control two articulation if is needed. Okay? That's thank you.